Hi and welcome to the presentation of the fast fiber line extraction for 2D bivariate scalar fields. My name is Felix and I will tell you something about our motivation and the idea in the first part of this talk. Following that, I will short present our evaluation cases and the results. Level set extraction from scalar data is a fundamental operation in visualization with many applications. Recently, the concept of level set extraction has been extended to bivariate scalar fields. Previous work on vector field equivalence, where an analyst marks a region in the domain with the control polygon and other regions in the domain with similar vector values are displayed. This results in control polygons with many edges, for which a fast extraction process is needed so that the analysts can work interactively. Let's consider a fiber as a possibility to analyze this. For this, we have a 2D domain and a 2D codomain, where the two values of the vector field each have one dimension. A fiber itself is a mapping of a point from the codomain into the domain. If we extend this and use a control polygon instead of the point, then we call this a fiber line. But the fast extraction is not free. Our problem is that extraction in bivariate scalar fields are not yet being explored. Also, the naive approach required too many operations and tests when computing the cell edge pre-image, which makes the algorithm slow. The idea is therefore to extend existing acceleration structures by using two bounding volume hierarchies. To find the pairs with minimal effort, we need to switch the two bounding volume hierarchies in a clever way. The approach that we extend is from Klakanski et al. This used a bounding volume hierarchy for all cells in the codomain and intersects the bounding box of the tree with the individual lines of the control polygon. If they don't intersect, the subtree is not tracked further, and subtrees that intersect the bounding volume hierarchy tree is further subdivided. This is repeated until you reach the leaves of the tree. This creates cell edge pairs, which are then used for the real extraction test. We extend this by creating also a bounding volume hierarchy for the edges of the control polygon and intersecting the two bounding boxes. We decide according to a certain strategy which bounding volume hierarchy will be further subdivided. And this is repeated until both bounding volume hierarchies are in the leaves. If the control polygon bounding volume hierarchy is reached the leaves, we use the line bounding box intersection test because it's generated less false positive cell edge pairs. A false positive cell edge pair is a pair that doesn't intersect in the real extraction test. Finally, we evaluate our algorithm in several cases. To do this, we use one analytic dataset, the double gyre, and three real-world datasets, the common vertex tree, the red sea, and the tensor bar. These have different codomains in each case. In the first case, we test the four datasets with 9 control polygons contain 3 to about 3K edges. The control polygons are randomly placed and used in 25 sizes. This results in over 184K test cases. An example of this case is shown on the left side for the vertex detection in the Red Sea, where the different vertices in the domain are represented by the purple fiber line. On the right side, you can see in the table the total time and TPAP, the ratio between the true positives and all cell edge pairs. You can see that we have a higher ratio and therefore a lower total time. In the second case, we test also the four datasets. And we used as control polygon 1001 isolines from a third variable. In total, we have 4004 test cases. An example of this can be seen on the left side for the stress propagation in the tensor bar. In the lower figure, you can see the codomain with the pink isoline as control polygon, and in the upper figure you can see the resulting fiber line in purple in the domain. In the plot on the right side, you can see that our algorithm is faster in comparison with the other algorithms, especially in comparison with the naive algorithm in PITROL. In the third case, we look at the field equivalences by linking two algorithms and executing them one after the other. In the total, we look at the 4 datasets and use a circular control polygon with 60 edges which we placed randomly. In this case, we have 404 test cases. An example of the common vertex tree dataset is shown in this figure. Here is the mean overall time resulting from the combination of the two total times below 40 milliseconds. This is 2.2 orders of magnitude faster than the naive algorithm. In summary, we presented an acceleration of fiber line extraction for 2D. We performed an extensive runtime comparison. We showed that our algorithm is several orders of magnitude faster, and we found that our approach works well for control polygons with many edges. Based on this, in the further we will reduce false positive cell edge pairs. Extensive field equivalence approach of Zen et al. To our method, and study the performance of our algorithm adapted to 3D domains. Thank you for your attention.